Hello, welcome. So in this series, we've been building a CPU from scratch, and so far it can do the Fibonacci sequence. And in the previous episode, we discussed setting up a proper assembler. So I have some good news. On this website, I talked about the wiki documentation being incomplete. Well, it's much more complete now. Yay! So I submitted some documentation, and I think it's a lot easier to just take what somebody else has written and just edit it a little bit and fix it up. So yeah, that's been done. It's a bit different than what I submitted, but that's very okay. In fact, I encourage it. So there is a little bit of a blurb on how the bits directive works. So that's neat. Neat. Yeah. So a bit of a directive on that. And then we've got data blocks, how this works. Neat. I didn't know you could do that. That's cool. Yeah. So yeah, I submitted some documentation and he improved it. So that's awesome. Yeah, working with banks. Banks are super neat. So yeah, great feature. The only thing that's missing is the expression syntax and how you would include like binary files. So for example, if you're making a game, you could include a picture that you want to display, and you can use these directives for that. I feel like this page is going to be a little bit more involved than the others, so maybe I'll sit down and write something up and see how it's improved by other people. So yeah, we'll see. In this episode, I'd like to move into building a bit of a test suite, and I must say this is the third attempt to do this. The previous two attempts turned into way too complicated. So the previous ways that I tried to do this was to build a circuit that would run a test suite, and so I could have a series of test programs loaded into the program memory, and it would try to run each one in sequence, and if they failed, then it would move on to the next one, or if it passed. That turned into quite a hairy mess. There was a really complicated state machine in the middle of it, and I don't like solutions like that. I've always regretted keeping them around. I'd prefer to just delete them, so that's what I did. I deleted it. But okay, so let's move right along here. Some of the first things that we do need to do in order to build a test suite, though, is we need to be able to verify our programs, that they're actually doing what we want them to do. And the simplest way to do that at this point in the processor's evolution, like we don't have conditional branches, we don't have really conditional logic of any kind. So the easiest way is just to add an instruction that does the verification. And so that's what I'd like to do. So I'll just start working on that. One of the things that I need to fix is we've got result mux here that's being outputted, and we have an op, and they're pretty much the same signal, just a little bit different decoded. Let's just remove this and just send the op directly to the execute unit. I think that makes a lot more sense. So yeah, let's do that. So I copied and pasted this just so I have a bit of a reference. The top one is add. So in the case of add, we want the sum to go in there. And in these cases, we don't care. But in these two cases, well, in this case, we want right to go straight through. So that's on 6. Straighten that out. And then for jump, we want the left to go out to the bus because we don't want to change the register. So that'll just put the value that's currently in the register back out. Okay. I'm not super fond of the way that this is reversing like that, but not sure how to fix it. Sort of like that. Okay. So we need a must eq instruction. In the case of the must eq instruction, I don't want to change any registers. So it'll be the same as the jump. So we can just do that. So must eq is must equals. It's an assert that the two values are the same, essentially. And the easiest way to do that is just to use a comparator. You can also check if two things are equal using XOR and then do a zero detect on the other side. If two values are the same, when you XOR, the result should be 0. So that's another way that you could do it. All right. So we need our left and right. There we go. And we have our equal operation, but how do we match it? Well, the easiest way is just to use a multiplexer and then pull out the correct line. And actually, I'm just going to label it so that it's a little bit more clear. And then what do we want to do? We want two outputs. One is if the condition is successful, and let's call this, I kind of actually want to call this halt and error. So halt means we're done with our test program. We can finish, it passed. Error means that the test has failed in some way. So we want to know that it's a must eq. In the case that is equal, we want halt. In the case that it's not equal, we want error. And that seems good. Let's test it out. Oh yes, gotta adjust the bits. That seems to work. Okay, so if we have instruction 5, if they're equal, then we halt. If they're not equal, then we error. Perfect. And then if it's not instruction 5, both of these stay low. Excellent. That's exactly what I want. So there we go. So we've got a bunch more signals now. So let's clean that up. Oh, and we should move the op down. So now we just need to make sure that the must eq will be displayed correctly. So it doesn't look like we've broken anything. Seems like it still advances, but we don't really have anything to verify this. So let's see if we can build out a program for that. So here's the program that we're executing currently. And what I did is I just broke the CPU definition out into a separate file. So this is what the file looks like. And you'll see that I've already put in the must eq instruction, and I decided against having a halt instruction. And this is now opcode 5, I believe. So we've got the ability to check if a register and a value are equal, and that's here. And we also have the ability to check if two registers are equal to each other, and that's here. So yeah, that's how that works. Otherwise, there's nothing different in here other than, oh, there's this label align, which we don't need anymore. So I have this. So then what I can do is I can have a separate test program, and this test program is, well, essentially testing the move and add instructions and checking if they equal a specific value in the end. And then we no longer need halt. Okay, sweet. So let's see if we can run this through our assembler. And I have also off camera done a bit of a makefile. So Make is just a program for helping you build software. So this is what I'm doing in order to build the Fibonacci program. And I'm just going to copy and paste that and build the add test. And then we just do, all right, like that. And then we can run that. Success. Okay. So it wrote it out to the digital hex file. Let's see if it runs. So it adds the two numbers. Mustique 10 equal 10. Yeah. So there's our Mustique, and it's saying halt. So if we change our program so that it fails, it's easy enough to do that here. And then we just need to make it again. Now, if we run the program, 10 Mustique 11, we get an error. So let's try and put this into a test case. So if you look in here, there's a test component that you can use. And you can give it a label. Let's call it add, because it's testing add. And you can edit. There's a very interesting set of documentation that'll let you read in your own time. I suppose you could try and read it by pausing the video. I'll scroll through it slowly. So one of the interesting things is it's got this program directive where you can load a specific program in the program memory. It is in machine language though, so I'd prefer to have assembly language test programs. So that's close to what I want. I'd prefer it to load just a hex file from disk, but well, we can work with this. So what I plan to do is just use this while construct here to wait until either the halt line or the error line goes high, and then assert that it was the halt line that went high and not the error line. So that seems like it'll work. So I built something off camera, and I hope it'll be okay if I do that because it involved programming. And I'm not sure what people feel about programming that are watching this. So I just dove into Ruby because it's a nice scripting language for doing these sorts of things. And I built a program that will essentially build those test cases for us. So what it does is it reads the test program, in this case it'll be this program, into memory. And argv is just take the first argument, so then we can run this program on any test program. Read it into memory, split it into lines, comment out those lines. So in the test case, a hash at the beginning of the line indicates it's a comment. So we comment out those lines and then join it all back together so it's one blob of text. And then we also take that same file and we run it through custom ASM to produce the Logisim 16 format. And just a reminder again what that format looks like. It looks like this. So we get this header that we need to strip off, and then we get a bunch of hex values. Well, that looks like really close to what we need for the program statement in the test case. So what I do is take the output, I then split it into a bunch of lines, and this syntax here just takes everything but the first line. So it strips off that header that you saw, it strips this off, and then it splits out the lines. So in this case, there's only a single line, but if it was a longer program, it would have multiple lines with hex values and spaces between them. So this will split those out into individual hex cases. So it'll split it on these spaces here, and we'll have just these hex values, but there'll be multiple lines of them. So it'll be an array of arrays. So what we want to do then is just flatten that out so that it's a single array, a single large array. So essentially it just takes a 2D array and makes it a 1D array. And then what we want to do is prepend the 0x, because if you recall in the help, the program directive here has 0x in front of each of the machine code instructions. So we want to add that on. And then we just take this template here. This is just a multi-line string. We tell the test case what signals we want. you say, okay, I only want to pay attention in this test case to the clock signal, the error signal, and the halt signal. I take the commented out program that I produced up here, and I just put it in there so then we can see what the machine language instructions are in assembly. Just makes it a little bit more self-documenting. And then we join all of the hex values with the 0x or 0x prepended to them. We join those all together into a single long list and give that to the program directive. And then we have this while loop that essentially checks if the halt line goes high, checks if the error line goes high, or checks that we've exceeded some maximum number of cycles that we expect the test case to take. In this case, it's just an arbitrary number, so I set it to 100. So this is just a catch-all clause to make sure that if the test program doesn't actually hit a must-eq instruction, that the test case will eventually fail instead of just hanging digital. So yeah, we increment I by 1 each time through the loop, and then we assert that all of the signals are low. In this case, what we're doing is we're driving the clock signal. So the clock signal is an input, so we drive it low and then we drive it high. In this case, inside the while loop, we don't care if the error signal or the halt signal are high or low. We ignore that so that it'll exit the loop, and it should exit the loop while the halt or error line are still high. So then this asserts that the error line is low and the halt line is high. So this line just asserts that the test case ended with a must-eq instruction that was successful, if that makes sense. So let's run this. And let's run it on the add test case. And did that work? It did indeed. So we get this output, and it read in the program and emitted our test case for us. So let's just copy that, and we can go into here and we can paste that in, and we can actually run the test and see if it'll work. Oh, we don't have a clock signal. Okay, let's just rename this clock and see if that fixed it. Clock is not found in the circuit. Okay, let's actually add a clock component. Let's rename this back to, and actually what we could do is just OR these together. Oop. Okay, that seems to work. And can we still, yes, okay. That worked. Oh, do we still have the fail? We do. So you can see here that the test case failed. What it did is it went through the loop a few times. You can see that with the I here. So I equals 1, it switched the clock, and in fact you can see a graph here, which is also neat. So you can see that the clock is pulsing up and down. It gets a certain number of cycles in, and then the error line goes high, and you can see here that when it exits the loop, the while loop here, the error line is still high, and the error line should stay high until the next clock going high. So as long as the clock doesn't go high again, it'll stay high. So you can see it was expecting the halt line to go high and the error line to be low, and it was not. So if we update our test case then here and we fix it and then rerun the script and take the new output, oop, a little sensitive to my mouse, they paste that in. Now it's 10, and we run the test, and you can see it passes now. So that means we can add a whole bunch of test programs, and we can add them as test cases, and it's going to add another one of these things for each test case. Right now we just have the one, but once that gets a little bit more cluttered, what you can do is you can create a new circuit and just embed this circuit in it. So let's test and make sure that that is going to work. I want to set up my colors here, and well, actually, let's name it what it's called. Okay. So if we take this and copy it, I'm going to delete it from this one. And if we go save, Okay, so we've got a fresh new circuit. Let's save it as test suite. Let's paste our test case, and let's also add as a custom our front panel. So we need to give it some inputs, and we can give it some outputs. I'm just going to go with this for now. Here, alt, and the PC is, I think it's 4. All right, that seems to work. So now if we run our test case, oh, I didn't name the clock input purpley. There we go. And it works. So then we can have as many test cases as we want in here, and it doesn't clutter up our front panel. And if we go back to the front panel, if we go into run all tests, it will run the test suite for us from here. So we can check and see if any tests fail. And if they do fail, we can just go back to the test suite and we can run the tests from here and see which one failed and which one's passed. So that is how we test this with some test cases. So this allows us to test with just regular assembly language programs, and I feel like this is a lot more readable than other ways of testing. But the testing language is very, very powerful that you can use. So we could actually unit test individual components and set up just basically a table test saying, I expect these signals at these times if this happens. This is more of like a end-to-end or a integration test. It tests that all of the components of the processor integrate correctly with each other. So this is definitely valuable, but we could go into here and add like some test cases to just test that, the add instruction itself executes properly and we get the correct bits in and bits out and all of that. So that is testing in a nutshell. So I believe this concludes this episode. If you have any questions, please leave a comment. Hopefully it was okay to not do any programming on camera and just show the script that I built to help with our test cases. Yeah, so thank you very much for watching. Have yourself a great day. Bye.